Okay, folks, we're taking off at example 6 here. Without a calculator, find the area of the region bounded. So I'm finding area. This is going to be positive. Maybe I'll highlight that or underline it at least. So this is where I've got to make a sketch and see if there's stuff that's below the x-axis so that I can make it positive. Find the area of the region bounded by the x-axis and the function y equals blah, blah, blah on the interval from -1 to 1. Use symmetry to help you evaluate the integral. So, yeah, I guess I can show you how to do it with symmetry, but I don't know if it really saves much time here. The big issue for this, I used to not do this problem because I looked at it and kind of freaked out. It's not as scary as it looks. Making a sketch is actually not as scary as it looks. So I'm going to encourage you to look for a couple of things with this function. I'm going to ask you to look for the end behavior. So remember, that's the limit of f of x as x approaches positive infinity, and the limit of f of x as x approaches negative infinity. I'm going to encourage you to take a look at what impact or what role the leading coefficient plays. I'm going to encourage you to find any problems. Let me get a different color here. Problems, or I probably should say discontinuities. I think I spelled that right. Discontinuities. And then, actually, well, what else do we usually study? We study the y-intercepts, the x-intercepts. I'll put that in the same color since they're related. And then oddness or evenness of the function. Okay, so I'm going to encourage you to pause, try to do some of these, fill out some of these things. These are all hints that'll help you be able to make a decent sketch. All right, so let's see how you did here. So my limit as x approaches infinity. So what happens here, you can think about this as putting in infinity for x. So as x gets bigger and bigger and bigger, what's a huge number squared? Still massively huge. What's a massively huge number plus another one? Well, give Bill Gates $1, right? He's still crazy rich, right? I should probably say Jeff Bezos now. I think might be the richest one. But anyway, when you have a massively huge number on the bottom of a fraction, what does that get closer and closer and closer to? 0. Now, if I pick a massively negative number and square it, it becomes even bigger, positive, and then plus 1 even becomes bigger, and so I've got another huge number on the bottom. So my end behavior, this graph needs to be approaching 0 as I go out towards the infinities. Notice our leading coefficient is negative. So that means that our graph is going to be, reflected. That's something we could talk about. Let's talk about problems. Problems occur when either roots, right, x underneath the root, we don't have that, or any x's on the bottom, we do have that. So I've got a problem here from our, back in our fundamental theorem of, first and second derivative tests. We've got a problem. But the problem is x squared plus 1 equals 0, x squared equals -1. That's imaginary. So this graph doesn't have any problems. Oops, sorry. That graph doesn't have any problems. Doesn't have any discontinuities. All right, my y-intercept. We find a y-intercept by plugging in who for x? 0 for x. So when I plug in 0 for x, 0 squared is 0, plus 1 is 1, -20 divided by 1, -20. Now, to find the x-intercepts, I plug in 0 for y. So if I put in 0 over here, well, the first thing I'd have to do is cross-multiply, which would kill this off, and it would say 0 equals -20. Not possible. None. There are no x-intercepts. And then remember, our graph is either odd or even, and we can test that by plugging in a negative in for x and see if our our equation comes out to be the same. So if I put a negative in here and I square it, what does that become? X squared. And so the whole equation would be exactly the same. That means this is an even function. which means it has symmetry over the y-axis. All right, so now pause again if you weren't able to make a sketch at that point, which I understand. I wasn't, like I said, the first time I tried this, I struggled. But now put those things all into play. See if you can make a sketch. So here's what I did. I said, all right, I know that my graph is going to have to level off at 0. I know that it has to be below the x-axis, or at least reflected, I should say. And I know that I've got a y-intercept of -20. So here's my y-intercept. How many x-intercepts do we have? None. So that means I can't cross the x-axis. I don't have any vertical asymptotes. I don't have any holes or jumps or anything like that. So the only way my graph could make this happen, now I don't know if this is a sharp turn or not. I'm going to draw it as a sharp turn. And so my graph is going to look something like this. Okay, so what's our boundary? Our boundary is from -1 to 1, so I'm just going to pretend this is -1. And I'm going to just pretend that that's 1. So the areas that we're trying to figure out are here and here. Now, what Corpy's talking about here is saying use symmetry. He's saying just integrate from 0 to 1 and then double your answer, because because this is an even function, they're reflected, so those two areas are going to be congruent, or those two shapes are going to be congruent. I would argue it's not that much nastier to actually just go from -1 to 1, but let's try to do it with symmetry. So we're going to try the method from symmetry. So I would like you to pause again and write up what you think the integral would look like if I wanted to calculate just this area here. Okay, let's see how you did. So first of all, this integral is below the x-axis, so I'm going to throw a negative out in front to make sure that it takes that. When I integrate that, I'm going to get a negative number. I want to flip that back to being a positive number. All right, so we're going from 0 until 1 of my curve, which is -20 over x squared plus 1 dx. So that's what your integral should have looked like. Now it's time to integrate this bad boy. First of all, I've got my constant. So a constant out front is just going to, it's just going to come out front. So a negative and a negative, that's going to make a positive. I'm blowing up over there. This is one of those trig functions you got to memorize. It's one of those inverse trigs. If you're one of those AP Calc test takers, and maybe even those who aren't taking it are starting to see it enough that it might be worth memorizing. But this one turns out to be tangent inverse. And we are going from, I'm just going to do the bar this time. I'm going from 0 to 1. Okay, so let's see if we can figure this out now. So now remember, it's plug, subtract, plug. So we've got 20. Actually, you try it. You try it. Pause. Try it. See how you did. 20, tangent inverse of 1. I'm going to use parentheses because it's kind of confusing. Minus 20, tangent inverse of 0. I'm going to go over here, I think. I'm running out of room. So we've got 20 times. This is asking you what angle, tangent inverse finds me angles, what angle, when I do tangent, gives me an answer of 1. So tangent's y over x. So where in the unit circle do you have a y value or a y side or an opposite side, and the adjacent side or the x side or the cosine side the same? Pi over 4. It's going to happen at pi over 4. Minus 20 times, okay, this is saying, and remember, tangent inverse, let me go back a little bit. Sorry, I probably should have mentioned this. Tangent inverse only lives in these two. So even though, what would it be? 5 pi over 4 also has a tangent of 1. It's outside of our defined domain. So tangent inverse of 0, so I'm looking for a place where y over x, where sine over cosine, is 0. So the sine or the y has to be 0, and the x has to be a number. That's got to be here. So that's at 0, right? Yeah, 0. Okay, so I clean this up. That's gone. That's 20 over 4. 20 over 4 is 5. 5 pi. Why am I not boxing in that answer? because we used symmetry. So we just figured out the first half. We now need to double this. So our actual area will be 10 pi. We don't have any units, do we? Good. So I don't like that pi. I wrote 11. Would be 10 pi. I don't like that pi either, but I'm going to live with it. So I'm going to write the word double in here. Must double. Because we went with a smaller region. Okay, let's see. All right, so here's the second part of the fundamental theorem of calculus. Now, like he said, most books call this the first part. I think it does make sense to do this part second. Okay, here's the idea. You're going to come up with some function, and this function is defined as the integral of some other function based on t. And look at our bounds. Our boundaries are, our lower limit is a constant. A is some constant value. Maybe I'll write a little note next to that says constant. So that's some known value, and then this x is our variable. So kind of the way you can think about this, so let's say I've got some sort of a curve. My curve looks something, I don't know, like this, let's say. Pretty exciting. And our boundaries, so this is going to be A. So then I'm going to pick, what's going to happen here is you're going to be able to have a bunch of different x values. So the area underneath the curve is going to change depending on what you put in for x. So this is going to give me a whole new equation or a whole new function that's based on these areas. So like, let's say my first x is here. Well, that means that my area then goes from there to there. And so my first area is here. And then I could also put in, I could extend that a little bit and go to x2. Now x2 is going to take that area, it's going to stretch it out, it's going to give me another value. So this is just going to, this is some input, that's my x value, and then the area underneath the curve is my output or my y value. I could go to some third x value, that's going to give me some input, and it's going to spit back some sort of output, and that output is that area underneath the curve. So that's what we're talking about when we're talking about this, the second part of the fundamental theorem of calculus. It's this idea that we can create a new function based on integrals that change. Let's see, anything in here that I wanted to talk about? Yeah, okay. All right, so let's take a look. The graph of f of t is given. So this is a picture of f of t. Actually, I'm going to highlight that. This is f of t. Let big F of x equal the integral from 2 to x of f of t. So I'm going to be doing a bunch of areas under the curve accumulating over time starting at x equals 2. And then I'm going to take those areas, I'm going to go forward, or I could even go backwards. Use the areas of the regions to find the following f of big 2's. Okay, so f of big 2, that's my big function. That's my capital function. So f of 2 would be like if I put 2 in here. Well, if I put 2 in here, what would I have to put in for x over here? I replaced x with 2, so that means I have to replace x with 2. So this is the integral from 2 to 2, and they didn't define the function any better than f of t, so we'll just call it f of t. Okay, let's evaluate this. This is our dream scenario. This is going from the area under the curve from x equals 2 to x equals 2. Well, how much area did we just cover there? In other words, our rectangle is 20 units tall, but how wide is it? It's 0 units wide, so that would be 0. All right, let's try the next one. You try to write it up first. So pause. What would f of 9 look like? Okay, so it should be from 2 until 9, f of 9, that means all the x's become 9s, of f of t dt. So now I'm going to find the area under the curve from 2 until 9. So that's from here to there. So I need to find all this area. Now, you could do the trapezoid formula if you think that's quicker. I think it's easier to break it up into shapes that I understand. So I'm going to drop a vertical here. Okay, let's talk about this area. How wide? 1, 2, 3, 4, 5 to the height of 20. So this has an area of 100. Okay, this is a triangle, 1/2 base. So the base is 2, so 1/2 of 2 is 1 times a height of 20. So this has an area of 20. So then what would be my calculation over here? If I wanted to figure out the area under the curve from 2 to 9, that would end up being, putting those together, 120. Okay, hopefully you're getting the idea. Why don't you try to do f of 15 on your own altogether? Let's see how you did. Pause if you haven't yet. So I'm going from 2 to 15, f of t dt. So I need to go, okay, I got that already covered. Now I need to go all the way here. So I need to now integrate this shape here. So you can probably, there's a, is that a trapezoid? I don't even really, with 2 slanted sides, that seems fishy to me, but whatever. I wouldn't worry about it. I would break it up into sections that I know. So let's see, this is going to be 1/2 of 1 times -10, that's -5, right? This is going to be the same, so I don't have to worry about that. That's going to be -5 as well. This is a width of 1, 2, 3, 4. 4 times -10 is -40. Okay, so I'm going from 2 until 15. So that's this area, this area, this area, this area, and this area. So 120, take away 10 is 110, take away 40 is 70. Let me try that again. Let's do it this way. 100 take away 40 is 60. Take away another 10 is 50, plus 20 is 70. Yeah, 70. Let's have you try f of 18. Pause it if you haven't yet. The integral from 2 to 18, f of t dt equals, okay, so now I need to figure out these areas. Well, this one's easy, right? It's congruent to these two shapes, except it's above. So that's going to have an area of 5. 1, 2 times 10 is going to have an area of 20. So now I want to add all those. No. You know what I'm going to do? I'm going to take this, 70, and I'm just going to add on those. That makes sense, right? Because the area under the curve from 2 until here is the same as the area, like basically I'm breaking up the integral. From 2 to 15, we already know is 70, plus another 25, so that's 95. And then let's have you try that last one there. Okay, so that's the integral from, okay, this time it's 2 to 0, f of t dt. Now, I don't like that. I like to fix that right away. Now, maybe you could just look and you understand it, you can go. I like to change that right away into the negative of 0 to 2 f of t dt. I do not like having those variables of integration backwards. So that means I need to go from 0 to 2, so that's going to be the same area as this. So that's going to end up being -20.